Um, so it's good to see everybody today. What I want to do today is I want to pick up right where we started off last time. So I think we ended class last time talking about this fundamental rule of counting. Do you guys remember that? And then I think if you guys remember, I gave a little bit of a fashion show for you about outfits. And then we did this example talking about stock names on the NASDAQ. Does that ring a bell to people? I got one yep. So what I want to do today is I'm going to pick up right where that left off. We're going to do a couple more counting methods, and then we're going to start this topic called discrete random variables. Just a few other things. If you look back in the classroom, you know, I said this last time, you have your homework number 3 is posted. If you look under course content, under week 6, I posted a bunch of old sample exams for you to review. So if you wanted to take a look at those over the weekend, you know, and maybe give them a shot or, you know, try some of the problems, you know, feel free to do so. And I can take questions on that next week. And then, so just one other couple announcements real quick here. Exam number 2 is going to be on Tuesday, 3/16. So that's, you know, going to come quicker than we think. So next week, what we're going to do is we're going to finish discrete random variables, start the binomial distribution on Tuesday. And then on Thursday, we'll finish the binomial distribution in the first hour of class. And then I'll do a review for the exam during the second hour of class. So does anybody have any questions about any of that before I get started in today's lecture? No questions? How many people took a little bit longer look at the homework since last class? Anybody? Is it not too bad, Melissa? Feeling a little good, not good? Not terrible. All right. So after class today, my hope is the only problem you won't be able to do is question number 7. So hopefully we'll get through everything so that you can do everything but question number 7. You might not be able to do question number 8. It just depends on how far we get today. Okay. But you'll definitely be able to do everything else on the exam or on this homework. All right. So let's actually start the lecture. And next week, I'll have a lot more time for questions on the homework and on the previous exams. And so one other, sorry, I'm a little scatterbrained today. One other thing you'll need today is have your graphing calculator handy with you. I'm going to show you how to use it to do some of the advanced counting methods we're going to talk about during the first part of class. Okay. So let's see. So last class, we learned about this fundamental counting rule. So today, really what I want to get through is 3 more counting methods, okay? And the next counting method that we're going to learn about is what's called the factorial, okay? And it's the exclamation point sign in mathematics, okay? So for example, it might be something that looks like this. 5 with an exclamation point behind it. Has anybody ever seen that before? Just out of curiosity. Nobody? You have, Julia? You've seen that before? It doesn't mean, yeah. It doesn't mean 5. Okay, like exclamation point. It's a mathematical operator. And that's okay if you haven't. It's actually very simple. Okay, so what we use the factorial for in this class, okay, is we use it to count the number of ways to uniquely select or arrange n objects. Okay, so we use it to count the number of ways to uniquely select or arrange n objects. So let me give you, that's exactly it, Julia. Yep. And it's super simple, okay? So n, what n is it's integer greater than or equal to 0, okay? So what that means is it'll be numbers like 0, 1, 2, 3, 4, 5. Okay, this factorial does not work for fractions or numbers with decimals, anything like that. So it's defined the following way. First off, if you have 0 factorial, okay, so I know this seems weird, but if you have 0 objects, okay, does anybody have a guess at how many ways you can arrange 0 objects? I know it seems weird. If you have 0 objects and I want to arrange them, okay, how many different ways could I do that? 0, okay. So this is where it gets a little confusing, right? So like, I'm going to turn on my camera here for a second. All right, can everybody see me okay on the camera? So if I have 0 objects, like I have nothing in my hands, right? The number of ways I can arrange 0 objects is this way, which is 1 way. So I know it seems silly, but the number of ways you can arrange 0 objects is 1 way. It's this way. So 0 factorial, whenever you see a 0 with the exclamation point behind it, it's always 1. 1 factorial is also 1. Like the number of ways you can arrange one object is just you stick it on the desk, it's 1 way. So then n factorial. All it is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Okay, that's it. So for example, 5 factorial here, this would be 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120 times 1. So if you have 5 objects, the number of unique ways you could arrange them, okay, is 120 different ways. All right, you ready to see an example in the context of counting of this? Okay. Here's the problem. Okay, and what I'm going to do is I'm going to introduce this problem, and it's going to kind of follow this fundamental counting rule. And you'll see, all over the place. And you'll see that it's going to end up just being the factorial. Okay. All right. So suppose Matt, okay, that's me, wants to make a playlist of his 10 favorite songs. Okay. So imagine like I have to go take a road trip or something and I want to make a playlist. I want to take my 10 favorite songs, favorite songs there, but my 10 favorite songs, and I want to make a playlist of it. Okay. I'll poke hits that. No, so Julia, this is not, this is just kind of going off of the PowerPoint from last class where there's no slides. This is just taking notes. And then when we get to the discrete random variable PowerPoint in about, you can see in like 4 slides, I'll load that up. Okay. This is just still taking notes freehand. Okay. All right. So here's the question. In how many different ways can Matt arrange the songs on his playlist? Okay. So imagine I've got this list, okay? And here are my 10 favorite songs, okay? We just have song 1, song 2, song 3, all the way to song 10. Okay. So you can actually solve this using the fundamental counting rule, okay? So if I have a sequence that I want to complete of n tasks, okay, and what my n tasks are is I have to select the 10 songs, okay? So think about this. How many songs do I have to select from for the first song in my playlist? Yep. Okay. Suppose I'm like, oh, I really like song 3. I want to start with song 3. I'll put that first. Then when I go to select the second song in my playlist, okay, how many songs do I have to choose from? Yeah, because I've already selected song 3. So maybe I want to put song 10 next. And then you're going to keep going. And then I'm going to have 8 songs to select for the third one, then 7, then 6, then 5, then 4, then 3, then 2. And then it's like, finally, oh, okay, I'll put this first song last. Okay, I'll get there in a second. I don't know if that's the answer. It might be. Okay. Do you see how this is just 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? This looks exactly like this factorial here. Okay, so you could write this instead as 10 factorial. Okay, does everybody see that? Give me a thumbs up if you see that, like or a yep in the chat. Makes sense? Okay.
Yeah.
All right. So here's the thing. Everybody grab your TI calculator, okay? I'm going to do it in both the TI-84 and the TI-83 here so you can see, all right? What you do not want to do, because it would be terrible, is go like 10 times 9 times 8. Like it would just, you don't want to do that, okay? So don't press this yet, okay? But on your calculator, it doesn't matter if you have the TI-83 or the TI-84 here. Okay, everybody look and see this button called math. You see this math button, math. If you press it, okay, oh, come on. Ugh, I hate this thing. If you press the math button, on the TI-83, you'll see this thing called PRB. Scroll over to that. And then on the TI-84, you'll see this thing called PROB. If you scroll over to there, does everybody see option number 4? It looks like this exclamation point. Does everyone see that on their calculator? Got one yes. So that's the factorial. Okay, so you can actually have your calculator do the factorial for you instead of going like 10 times 9 times 8, which would be terrible. So when you go to do this, okay, for this one here, it's 10 factorial. I want to find the total number of ways I can arrange my 10 songs. On either calculator, what you're going to do is you're going to go back to your main screen. And everybody type the first number first. You're going to go 10, and then over here, you're going to type 10. And then what you're going to do is you're going to press the math button. You're going to scroll over to PRB and then go down to 4. Or over here, you're going to press the math button. You're going to go over to PROB. You're going to go down to 4. And you should see 10 exclamation point. So when you hit enter, how many people who are following along got this number right here? Got it. Yes. Okay. A little bit easier, right, than going 10 times 9 times 8 times 7. You know what I mean? Like a little bit, yeah, it's so much easier and faster. All right, so it looks like, and this is crazy. This number is correct, and it does get big really, really quickly. It looks like if you have just 10 songs, the number of unique ways you can arrange them is 3,628,800 ways. Holy cow. Is anybody surprised how big that got so quickly? Yeah, it's the right number. It's totally the right number. And these combinations or unique ways you can select things are, these numbers get large really, really quickly. Okay. And if I were to make a playlist of the songs in my house these days, it would be Broadway hits for some reason. Okay, that's what we listen to every morning. It is fun. It is fun. All right. So I don't want to spend too much time on the factorial. I actually want to move into our final two counting methods. Okay. The reason I introduced the factorial is because our final two counting methods have the factorial in their formula. Okay. So is everybody okay if I go to the next slide? Anybody need to copy anything anymore? Okay. And our final counting methods are these things called permutations and combinations. Okay, permutations and combinations. And what we're going to use these for is the following. All right, the number of ways you can select R objects from N objects. So what that means by R and N, going back to my playlist example, it would be like, all right, I have 10 songs, but I only want to make a playlist of 5 of the 10. Okay. So you're going to select R objects from N. Okay. In which so you have to have the following criteria to use these combinations permutations formula. Okay. 1, R, this number has to be less than or equal to N. Okay. What I mean by that is like, you can't say, what's the number of ways to select 15 objects from 10? It's like, well, there's only 10 objects. How can you select 15 of them? Okay. The second rule, once an object is selected, it cannot be selected again. Okay. So what I mean by that, going back to the playlist example, it's like, if I want to make a playlist, if I have 10 songs and I want to make a playlist of 5 of them, I wouldn't make a playlist of the same song 5 times. Okay, that's what that other one means. Okay. Third, each object is unique. So each of my songs in my playlist is unique, and this is where it diverges. You'll notice I have this thing called permutations and combinations here. So there's 4A and 4B here. The first is if order matters. Okay, so the order that you select the objects is important. Okay, for whatever reason, the order is incredibly important. All right. For this, we use permutations. And the formula looks like this. It has n subscripted with a p and then an r subscripted on the other side, okay? So this is read as npr or npick r objects, okay? So NPR, I know it's like a radio station, but like it's n pick r objects or n permutations of r, okay? In this formula here is just n factorial divided by n minus r factorial. Now, the second way is if you have n objects and you want to select r of them, and the order doesn't matter. Okay, so the order of selection or the way that the objects are arranged or selected, it just like it doesn't matter. Okay. If that's the case, you're going to use combinations. Okay. And that formula just goes like this. It's NCR. So this is read as N choose R objects. Okay, N choose R. And this formula is given as N factorial divided by R factorial times N minus R factorial. All right, I have some good news, bad news with this. The bad news is, does the formulas kind of look a little complicated and hard to work with here? Or, you know, do you think they're not too bad, but would prefer, you know, think it's okay? Anybody would like, I'm with you, Alexandra. I see this and I'm kind of like, So that's the bad news, right? You got these crazy formulas here. But the good news is, we can actually use our calculator to solve all of these. Okay. So what I want to do is, I just want to do a couple problems by hand, show you how to work them out by hand. And then I'm going to show you how to use your calculator to get these. And you're always welcome to use your calculator on these. So we'll do them by hand and then just verify that our calculator gives us the same answer. Okay. Everybody okay if I move on, or does anybody need to keep copying?
Go ahead.
Go ahead. Thank you. Anybody else? I don't mind pausing. It just gives me a chance to finish my coffee. Okay. So this is permutations and combinations by hand. And I'll put this here, okay? Little frowny face, because, you know, if you can use technology, let's use it, right? All right, so let's find this one first, okay? Let's have 10 objects, and you want to pick 5 of them, okay? So just remember, this is my NPR, okay? So it's just n factorial divided by n minus r factorial. Okay, so it looks like here, the n is my 10 and the r is my 5. So this would be 10 factorial. Sorry, I'm a little bit of a crunch here. 10 factorial divided by 10 minus 5 factorial. So 10 minus 5 gets me 5. So this is 10 factorial divided by 5 factorial. So the way you would do this, if you wanted to do this by hand, is you would literally write 10 factorial out. It's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. What do you notice cancels out when you do this by hand?
5, 4, 3, 2, 1.
5, 4, 3, 2, 1. 5, 4, 3, 2, 1. You're gone. And so this is just 10 times 9 times 8 times 7 times 6. And then you can grab your calculator here. Like you can go 10 times 9 times 8 times 7 times 6. Oh. And so if I have 10 objects and I want to arrange 5 of them in which the order of selection matters, it would be 30,240 ways. All right, let's just do this one next, okay? Let's do 10 choose 5 now. And then after we do this by hand, I'll show you the calculator and then we'll get that going. So the formula for n choose r was n factorial divided by r factorial n minus r factorial. Well, this is my n, this is my r. So this is 10 factorial divided by r is 5. So 5 factorial times 10 minus 5 factorial. So Julia, that's a fantastic question. So this is just working it by hand. I'm going to show you with the examples how you discern if the order matters or the order doesn't matter. Okay, that ends up being the hard part of the question, figuring that out. So I'm just trying to just get through these examples by hand so that we can get to the more interesting stuff. Okay. So this is 10 factorial divided by 5 factorial, 5 factorial. So look, you can write this out. This is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 5 factorial is again 5 times 4 times 3 times 2 times 1. Another 5 factorial. And look, cancel, cancel. This is 10 times 9 times 8 times 7 times 6, which we know is 30,240. And 5 times 4 times 3 times 2 times 1. We did that. It's 120. So if you grab your trusty calculator, it would be 252. So very different numbers here. Okay, that's why it's the same N and R, but you get vastly, vastly different numbers. Okay, so the reason I went through that so quickly is doing it by hand is terrible. And you know what? I don't even like to do it by hand. Okay. So let's grab our calculator and let me show you how to do this with your calculator. Okay. So let's do this first with our calculator. Let's do this 10 pick 5 with our calculator and see if we get the same number. So don't press this on your calculator yet, okay? I just want to show you something. When you press the math button on your calculator and go over to PROB, and over here, it's the same thing, PRB though. Do you guys see option 2 and 3 there? Does everyone see NPR and NCR, NPR and NCR? It's amazing. Your calculator does this for you, okay? So if you want to do this by hand, what you'll do on your calculator, okay? If you want to do 10 pick 5, start by typing in the first number, which is 10 on your calculator first, okay? Then you go to math. You go over to PROB. You scroll down to option number 2 and you hit enter. So over here you go math. PRB, you go to option number 2, you hit enter. And then you type the second number, which is 5. And notice how the calculators show them a little differently. But look, did we get it right when we did it by hand? Yeah, but
Professor,
yeah.
I have a question. What if you do NCR instead of NPR on the calculator?
We're gonna do that next. We're gonna do that
okay.
next and show you. So let's do the NCR. Okay, it's the same option. So you're gonna put 10. It depends on which calculator you have, Melissa. If you have the TI-84, you can actually do that. If you have the TI-83, it's a little bit different. That's why I just show it this way. Just so I can just do it once. Oh, shoot. So you're going to go 10. You're going to go over to math. And now we're going to do NCR. And then you're going to put the second number. And look, did we get it right by doing it by hand? Yes. But is it a lot easier with the calculator to do it? What do you guys think? Calculator's awesome. Yeah, that's why I call it the trusty calculator. I never let you down. Okay. Every time I needed a ride to the airport, it was always there for me. That was a bad joke. I'm sorry. I couldn't resist telling it though. It never disappoints. Never disappoints. Yeah. Okay. So there was a great question. I think it was Julia who asked it, who said, how do we know if it's order matters, order doesn't matter? Okay. And you're going to have to figure that out by discerning that information from the problem. All right. So everybody ready to see some examples, and it'll be up to us to figure it out? Okay. One, two, three. 1, 2, 3. Okay. Just want to make sure I have enough slides left. 1, 2. No. Okay, I don't. Okay. This is an example about racing. So I'm going to give you a little bit of personal information about me that we'll use for this example. Okay. So I grew up in upstate New York. I grew up outside of Albany, New York. I grew up near a place called Saratoga Springs. Does anybody know what Saratoga Springs is famous for? It's famous for a couple things, but does anybody know what Saratoga Springs has in it that it's like its main attraction? It does have natural springs, yes. That's it. The two right there are the big thing. It has the country's oldest horse racing track. Okay. I don't, it is a hot button topic because there's a lot of animal rights issues. I don't want to get into that, but I will just say this. It is a very unique experience, and I grew up going every summer. But so, and to be honest with you, it is worth the trip if you've never seen it. It is really cool. And Saratoga Springs is like such a beautiful little town. But anyways, so here's the problem. Okay. This problem is about betting on a race. Okay. I'm just curious, has anybody ever been to the Saratoga horse track? No, it's okay if nobody has. Once. Did you like it when you went, just out of curiosity? I think it's pretty cool. Yeah. Okay. So when you go to the horse track, you can gamble on the races. I'm not advocating for gambling or not gambling, just so we're clear. But there's this bet you can make. There's these two different bets you can make. There's something called a perfecta bet, and there's something called a trifecta. Okay. And what a perfecta bet is when you go to the counter and you go place your bet, and if you put a perfecta bet, it means what you're doing is you're picking the top two finishers in the race. So what do you think a trifecta bet is? If a perfecta is picking the top two, what would be a trifecta? Yeah, you pick the top three. Okay. So the reason I like this example, because this is a little, I have two young nephews and we would go growing up. And I remember one time we went and I was betting, I was making these bets with my nephews. We'd give them like $20 and they would, play the horses that day. And so I always like to make these bets because I think they're fun. But anyways, we would lose. Like, I'm not a good gambler. Okay. And so we would lose these bets. And my nephew said, we had this race that came up. Okay. And it was a 12-horse race. My nephew said, you know what, Uncle Matt, I'm sick of losing. Let's pick every possible perfecta bet so that we guarantee we win. Okay. So in a 12-horse race, first question is this: how many possible perfecta bets are there? Okay, so here's what you have to ask yourself here. Okay, how many horses are there in this race? How many? Yep. Okay, so that's my n. That's the total number of objects. Okay, and if I want to do a perfecta bet, okay, how many horses do I need to select? Yep, you need to pick the top two. So the next thing you have to ask yourself is this. Okay, this is really what it comes down to. Does the order matter or does the order not matter here of selection? So think about it in a race. Okay, here's the thing. In a race, does the order matter?
Yes.
Yes. Yeah. Okay. So here's the thing about the perfecta bets that I need to make clear. Suppose you have two horses, and if you've ever been to the horse track, you know they name their horses. So one horse is like Seabiscuit, and the other horse is Warhorse. Okay. If I select my perfecta bet and I say it's going to be Warhorse Seabiscuit, but what ends up actually happening is Seabiscuit comes in first and then Warhorse, I lose because I didn't get the order right. Excuse me. So does order matter here?
Yeah.
Yeah, order matters. Okay. So then you have to ask yourself this: is it a permutations or combinations problem?
Permutation.
It's permutations. Okay. So all this is you have 12 horses and you want to pick the top two. So you can grab your calculator and you can just go 12, math, scroll over, option number 2. I have 12 horses. I want to pick the top two. There's 132 ways to do this. Okay. So I had to tell my poor nephew, guess what? I'm sorry, we can't do 132 tickets on this bet. Okay. So now let's do the trifecta. Okay. In a 12-horse race, how many possible trifecta bets are there? All right, well, how many horses are running this race? It's still 12.
12.
Yep. And for a trifecta bet, how many finishers do I have to pick?
3.
Yep. And again, with things like races, order matters. So it's a permutations problem. Okay. So this would just be 12, pick 3. So you go 12, math. And this would be 1,320 different tickets. Yikes. So generally on the exam, things that have like races, okay, those are going to be permutation problems. Okay. Everybody ready to see the next example? Okay. All right. No. Let's make a conference selection. Okay. So here's the problem. Okay. The math department at WCC has how many? I think it has 16 full-time faculty. Of which 9 are females and 7 are males. Okay, that's the composition of our math department. Okay. So I've got a couple questions for you here. Okay. And it goes like this. This is suppose 2 faculty are to be selected to attend a conference in Las Vegas. Obviously next year post-COVID, okay? All right, we'll just say it like that, okay? So here's the first question. How many different ways can you select 2 faculty to go? So basically, this is what's going on. There's 16 full-time members of the math department. And we just want to know how many different ways can you select 2 faculty to go to this conference in Las Vegas? Like imagine they're going to pick people at random to go to this conference, okay? And it's an awesome conference. Everyone wants to go. It's at the Bellagio. You get to see the water fountains. It's a fabulous time. Okay. So how many total faculty are there to pick from for this? Yep, there's 16. And how many are we selecting to go? Yeah, okay. So it's an N and R problem. So the next thing you have to ask yourself is this, okay? Does order matter? Does order of selection matter or does order not matter? Okay, Julie, why does order not matter? You're correct. Do you have a guess?
Because it can be like any combination, I guess, of, I don't know how to explain it.
You're absolutely right. So you have to ask yourself this question, right? Okay, if I'm selected first or second, am I still going to get to go to the conference?
Yeah.
Yeah, so it's like, I don't care about the order. I just want to get selected to go. So here the order doesn't matter. The order is not important. Okay, so when order is not important, is it a permutations or combinations problem?
Combination.
Yeah, yeah. So this would just be 16, choose 2 faculty. So you're going to grab your calculator. You're going to go 16. You're going to press the math button. You're going to go over to PRB. It's option number 3. And it's 120. So there's 120 different ways. So do you see the subtle difference? Like for these problems here, it's like committee selections, things like that. Don't order of selection doesn't matter, whereas racing, the order does matter. Okay. Does it kind of seem a little bit clear about the this is combination. So when the order is not important, Bertha, it's combinations. All right. Let me ask you one more question related to this example. Okay. So I'm going to ask you a probability question now. What's the probability two females are selected to go to Las Vegas? Every time I say Las Vegas, I get that song stuck in my head. Viva Las Vegas. Okay, sorry. I hope that made one person laugh at least. I have no idea how to do this problem. I'm glad you laughed, Alexander. Thank you. So I want to find the probability that, so it's a probability, okay? So it's going to be a number between 0 and 1, right? Like I think what you did there was you did a little multiplication. That's okay. Like, oh man, this is like, so I want to find the probability 2 females are selected to go. Does anybody, I know I'm being silent. Does anybody have like a guess of how you could tackle this problem? So what you did there is just, so you could do it that way. Okay. I know exactly what you're thinking. You would do 9 over 16 times, 8 over something. But what I want to do is I want to show you a different way using these combination ways to tackle this problem. Okay. So watch, this is just a simple division problem. Okay. What goes in the numerator is the number of ways to select 2 females. And what you divide this by is the total number of possible selections. So watch, this is actually really, really cool. Okay. So to figure out the number of ways to select 2 females, okay, how many female faculties are there?
9,
And how many do I want to select?
2.
2, right? So ask yourself this. I have nine female faculty members and I want to select 2 of them, okay? Does the order of selection matter? What do you guys think? Like if you're selected first or second, do you still get to go? Yeah, it doesn't. Yeah, you still get to go to the conference. So this is just 9 choose 2. And did we figure out already how many total number of possible selections there are? What do you think? How about this right here?
120.
Yeah, it's just the 16. There's 16 choose 2. Yeah. So we already know that 16 choose 2 is 120. So we just need to find what 9 choose 2 is now. And it looks like it's 36. So 36 divided by 120. Looks like there's, yep, thanks, Alexander. Yep, 30% chance, so 0.30. What do you
Professor, I
think?
have a quick question.
Of course, of course.
So I've noticed that NCR would mostly be for all combinations, right? And then the other one, like on the calculator, let me see. The other one, NPR, would be like for permutations, right?
Always. Yep, always.
Okay, thank you.
Professor,
Yes.
so permutations is when the order does matter, and then the what is it? Oh, combination is when it doesn't matter.
That is absolutely correct. Okay. Yeah. So let me just do one last example, and then we'll take a short break. Does that sound okay with everybody? Okay. And this is about my current retirement plan, okay? And my current retirement plan is winning the Powerball lottery. Okay, have you guys heard of this Powerball lotto before? All right, so let's see here, just real quick. Like, what is the Powerball jackpot even? Let's see. The Powerball jackpot currently is, I don't even know what it is right now. I think it's 100-something million right now. Oh, it's 123 million. Okay, getting drawn tomorrow. Okay. So here's what I'm going to do after class, okay? I'm going to go down to the local shop, local store here. And what I'm going to do is I'm going to buy one lotto ticket. I'm going to buy one Powerball ticket, okay? So what's the probability Matt wins Powerball on Wednesday with a single ticket? Maybe. So I'm just going to buy one ticket. Okay. And it's not zero, it's non-zero. And basically what another context of this question is what's the probability you have a different instructor on Thursday? Okay. That's a joke. I will finish out the semester. Okay. I will torment you with bad jokes until May. Okay. All right. So in all seriousness, let me, I got to explain to you how Powerball is done. Okay. Or what constitutes Powerball. And then we'll figure out the probability I win with my single $2 ticket. Okay. So the way Powerball works is this. Has anybody ever seen a drawing of a lottery live? I'm just curious if anybody's actually ever seen it. So the way it works, yeah. So the way it works is I'm going to turn my video on just so you can see like me explain this. So what this works is they have this big cage, as Melissa said, of balls, and they spin the balls around, and then the balls come out of the cage at random. Okay. And so the way it works in Powerball is you have one cage of balls. So here's the cage. Okay. And it's spinning. Okay. And it has the balls numbered 1 through 69 in it. Okay. And what you have to do is you have to select 5 numbers from here. Okay. It turns out if you do that correctly, if you select these 5 numbers from here correctly, you actually win $1 million. Okay. So what you have to do in addition to that is there's another cage, okay, which has what's called the Powerball number. So there's another cage here and it has the balls 1 through 26 in it. And you just have to select one from here. Okay, that's it. That's all you have to do. Like, that's it. Okay. So all I have to do to win the lottery and buy my dream house down on the Jersey Shore is just select 5 numbers from there and 1 from there, and whoop, that's it. I win. Okay. Seems super easy, right? Everybody at least kind of got the process of the Powerball done. And then now we're going to figure out the probability I win with a single ticket. All right. Everybody good with at least how you play Powerball? I got one yep. I got a couple yeps. Okay. So I'm going to go to the next slide. And what we have to figure out is the probability I'm going to win with my 1 ticket. So it's a probability Matt wins with 1 ticket. Oh man, I can feel my dream home coming. Okay. All right, so it's a simple division problem. Okay, so what we have to figure out in the numerator is the number of ways to win with 1 ticket. And then what do I have to put in the denominator here, do you think? The total number of possible what? Total number of possible tickets. Would you guys agree that the denominator is the total number of possible tickets that are out there? So it would be something like this. If I were to go pick these numbers, 2, 3, 22, 28, 60, and then my Powerball number would be the number 5. Okay. So it'd be like, this is the winning ticket. Wouldn't it be amazing if actually on Wednesday, this was the winning ticket number? That would just be wild. Okay. So if I'm going to buy 1 ticket, what's the number of ways I can win with 1 ticket? Does anybody have a guess? The number of ways I can win if I only buy 1 ticket? Yep. It's 1 way. It's that, like, this is the winning number. If this is my ticket, there's only 1 way. Okay. So now I need to figure out the denominator. This is the hard part here. Okay. This is the really hard part. I don't know. I have no idea. This is weird. Anybody got a suggestion? Seriously, anybody, like what they think? I don't know. All right, well, let me help you. All right. So going back, here's the first thing I need to do. I have this sequence I need to complete, okay? So I need to first figure out the number of ways I can select the numbers from here. Okay, so the first thing I need to figure out is the number of different ways I can select 5 numbers from 69. That's the first thing. That's it. That's all I have to do. I just have to select 5 numbers from there. And then the fundamental counting rule is like, okay, well, then I would just multiply it by the number of ways I can select one ball from these 26. Well, look right here. How many numbers do I have to select from the first cage of numbers?
$69.
Yep. And how many do I want to select? What's my R?
5.
Yep. So it's an N and R problem. So all you have to do is figure out, does order matter? Does order not matter?
Yeah, it does.
Okay. Anybody disagree?
Oh wait, I don't know. Do you have to get them in? I forget what you said. If you have to get them straight or just any combination.
So here's why I ask if anybody's seen it live. Okay. When they select the balls at random, okay, do they come out in numerical order or do they just come out in a random order? Yeah, the balls just come out in a random order. But what they do when they tell you the winning ticket, what they do is they just put the orders in number for you, or they put the orders in sequence for you just because it's easier to look at. But like if suppose they say this is the winning lotto ticket, but I fill out my lotto ticket strip and I say, oh, I like the number 22. Oh, definitely 2 and 3 and 28 and 60. Like I still pick the winning numbers. Okay. So the order doesn't matter here. So is that a combinations or permutations problem? What do you think?
Combination.
Yep. So the first thing here, I have 69 numbers and I want to choose 5 of them. And I would multiply that. Don't overthink this. Okay. If you have 26 numbers to choose from and you just want to select one number, how many different ways could you do that? If there's 26 objects and you just want to pick one of them. What do you think? Well, do you want to select one number, but how many options do you have to pick? You're on the right track, Brianna. You just think of it a little differently. If you have 26 numbers and you want to select one of them, the number of different ways you could do it is just 26 different ways, right? Because there's 26 numbers to pick from. So now look, now we can figure this out, okay? So the probability that I'm going to win Powerball tomorrow with my one ticket is 1 divided by, so we got to figure out what 69 choose 5 is. It's that many ways, and then times it by 26 because there's 26 different Powerballs to pick from. So the probability I'm going to win Powerball with my one ticket is 292,201,338. What do you guys think?
Professor,
Yeah, going ahead.
I have a question. Since you said that it was 26 for the second denominator because there's different, like it's a select one from 26. What if it said select two from 26? Would the denominator still be 26?
So
Or?
if you had to select 2 from 26, assuming the order doesn't matter, it would then just be 26, choose 2.
Oh, okay. All right. Thank you.
Yeah, like if you plug into your calculator 26, choose 1, you're going to get the number 26. Can you repeat the process? Sure. So you want me to do the, so the first thing I had to do was I have 69 balls. And I want to choose 5 of them. So I just hit enter. And then I had to just take that by, multiply it by 26. And that's how I got that number. Did that? Good. Good. All right. So am I going to be able to get my dream house at the Jersey Shore tomorrow? Am I going to be able to retire?
Probably not.
Probably not. Non-zero chance though. You know, somebody has to win. Somebody wins. So why not me? Right? You never know. Why not me? Okay. All right. So just to let you know what the type of questions will be on the exam. I like to do the Powerball example just because I think it's fun. But the questions that'll be on the exam will be like a race example or a committee example. So just realize the difference there. Okay. All right. So I went a little over, but let's take our break now. All right. Does that sound okay? Break good with everybody? Okay. All right. So look, I'm going to come back from break at 2:15. Okay. So let's do break until 2:15. So I'll see you guys in a couple minutes. Okay. All right, can everybody hear me okay? Gonna get started again in a couple seconds. All right. So this PowerPoint was put up in the folder here. I'm sorry that some of my slides ran over. That was just poor planning on my part, so my apologies for that. But is everybody kind of ready to get away from probability for a bit? Yeah, I understand. I know I say this, probability is a weird concept. It's just difficult. I understand. I will say this though. When it comes time for the exam, there are no, to stick with the baseball reference, I'll put my video on here. There are no curveballs. I said a baseball for some reason. There are no curveballs in the exam. So, it's just basically the topics and the type of problems we've done in class, just different numbers, so it's, I don't stress too much. And I do think it's pretty manageable. Okay. So now we're going to start talking about discrete random variables. Okay. So first off, let's talk about this. Have we heard the word discrete before in this class? Does anybody remember what like a discrete data or discrete variable was?
A count.
Yep. So it's a quantitative data variable. Okay. So we generally refer to these as counts. Okay. And now we're going to begin our study of random variables. We're actually going to talk about random variables for like a month. Okay, it's going to seem like it never ends. But when you hear the word variable in mathematics, what letter do you associate with that? Yeah, thank you. So the thing is, in random variables in statistics have a different meaning a little bit. Okay. So we're going to tie random variables or this variable X to what we call a probability distribution. So we're going to spend a lot of time talking in the coming weeks about this concept of a probability distribution. So we're going to start with discrete probability or discrete random variables. We're going to actually go through it really quickly. There's not as much to study with them. And then we're going to spend a ton of time on continuous random variables. Okay. But anyways, let's go into this. What exactly are random variables in statistics? Okay. So let me give you a definition. Okay. So in statistics, a random variable. So random variable is a quantitative variable whose value depends on chance. Okay. When you think about mathematics, right? So a variable represents, and the variable X represents some unknown value. Okay. Some unknown value. And what we're saying here is, look, these unknown values, the value that comes up for this random variable, it just depends on chance. Okay. So there's going to be two types of random variables we're going to study in this class. There's going to be discrete random variables. Okay, so discrete random variables, what they have is they have a finite number of values. And then we're going to spend much more time talking about continuous random variables. Okay, and these have an infinite many values, or infinitely many values. Okay, so generally, as was pointed out, discrete random variables tend to be counts, and continuous random variables. Does anybody remember the M word that we use to describe continuous random variables? Started with M and ended in measurements.
Measurements.
Yes, thank you. I hope you guys liked my joke there. Okay. Actually, my jokes are pretty terrible, but I'm a dad, so that's okay, right? This is hopefully where everybody says, yes, that's totally okay. All right, is everybody okay if I, thank you, Alexandra. Is everybody okay if I move on to the next slide? Okay, yeah, no problem. Sorry, I tend to go a little fast. Okay. So let me give you some examples of these discrete random variables, okay? So the first one would be the sum of dice when a pair of die are rolled. Okay, so does anybody remember what casino game this was? We talked about this while ago, actually a couple lectures ago. So you're going to throw two dice. Yep, it's a game of craps, right? Like, so the game of craps, there's a finite number of outcomes in the game of craps, okay? And what we saw here was that each outcome was determined by chance. Now, some outcomes are more likely than others, but the value that comes up when you play this game of craps, it's totally determined by chance, okay? Another one that might seem a little bit different would be like the number of puppies in a litter. Right? Like you can count the number of puppies that are in a litter, right? And like, you know, the number of puppies that you know come in a litter, it's totally random. Like it's just by chance. Like is it 5 puppies? Is it 10 puppies? Like that's just the way it is. Okay. Or another one that we've looked at before would be the number of heads observed when flipping a coin 3 times. Like if you flip a coin 3 times in a row and count the number of heads, you can get 0 heads, you could get 1 head, you could get 2 heads, or you could get 3 heads, okay? So there's a finite number of outcomes in that case, they're counts, and the outcomes are all determined by chance, okay? So these are the type of examples we're gonna work with a bunch in this section, okay? So all finite number of outcomes, counts, and everything is determined by chance. All right, is everybody okay if I go to the next slide? Okay. So what we're gonna do, what we're gonna spend a ton of time on in the coming weeks is this thing called a probability distribution. Okay, so what exactly is a probability distribution? So let me give you the definition. the probability distribution of a discrete random variable and we're going to denote the discrete random variable as X. And don't worry, we're going to do a ton of examples of this. So, and let me just pause. And I know I've said this before, but have you guys ever noticed that sometimes in this class, I'll put a formula or definition up there and it'll be like, that makes no sense. And then once we do like 1 or 2 examples, it starts to click. Have you guys noticed that a little bit in this class? I don't know if that's true or not. Okay, one yep. This concept of these probability distributions, I'm going to put the definition up there and it's going to be like, oh, what the heck? But then after you see 1 or 2 examples, it's like, okay, I got it. Okay, so the probability distribution of a discrete random variable X provides all the possible values of X so all the possible values of the random variable and their corresponding probabilities. Okay, so it's going to list all the possible values and then it's just going to show their corresponding probabilities. So there's just a couple rules that we have to have. And these are the only rules you need to have. The probability of any random variable coming up has to be between 0 and 1. Okay, that's it. You can't have probabilities less than 0. You can't have probabilities greater than 1. And if you sum up all the probabilities of the random variable, they just have to be shown as 1. Okay, they just have to equal 1. And in this class, probability distributions can be shown as the following ways. They can be shown as a table. Okay, and this table is really what you're going to see in this section. It's going to be a bunch of tables. I'm going to show you the tables to show these probability distributions. The second way is going to be with a graph. And this graphical analysis is going to be very much shown in next section. And what I mean by the next section is if you remember, I broke the class down into 5 sections. So this concept of a graph to represent a probability distribution is going to come up after the next exam. It's going to be like the main, how we're going to show these probability distributions, with our next major topic. And then finally, you can show probability distribution with a mathematical formula. And we won't do that too much in this class. We'll do it a little bit when we talk about something called the binomial probability distribution, but otherwise mathematical formulas won't come up too much. Okay. So like looking at this, is it like a little confusing, like what the heck I'm talking about? You can be honest. If anybody's still paying attention, I hope. Okay, yeah. Just a little, like it's a little weird. Like, what do you mean it's a table that lists all the possible values of X and their corresponding probabilities? Like, it's just weird. It's weird. So what I want to do in the next slide is like, this definition is weird. Let me like show you what I'm talking about. Because after you see that, like it'll make sense. So is everybody okay if I go to the next slide? Everybody good? So the first one here, I'm not going to tell you what it is, actually. I'm just going to show you, and then you guys are going to be like, oh, I know what this is. Okay, so what is our random variable here? So generally when we do these problems, we're going to let x be equal to something, okay? So I'm not going to tell you what the example is first. So a probability distribution, okay? It lists all the possible values of the random variable x and their corresponding probabilities. So I'm going to show this probability distribution as a table. So generally what these tables do is they're a 2-column table, and it lists all the possible values of x and their corresponding probability, okay? So this random variable can take on the values 1, 2, 3, 4, 5, and 6, and their corresponding probability. So the probability you get a 1 is 1 out of 6. The probability you get a 2 is 1 out of 6, and so on. Every single one is 1 out of 6. Does anybody have a guess what the random variable x is here? So what have we talked about in this class can take on the values 1 through 6, and the probability that a 1 comes up is 1 out of 6. The probability of 6 comes up is 1 out of 6. Yeah, it's just a die roll. So we're gonna, what the random variable x is, it's gonna be equal to the result on a die roll. That's it. So would you agree that there's a finite number of outcomes and that the outcomes you get are determined by chance? Totally. So look, this is all this probability distribution does. I list the possible values of x and their corresponding probabilities. Done. Okay, I got it. So does that kind of like make sense for a probability distribution? At least not too bad. Just list the possible values of x and their corresponding probabilities. Piece of cake. Okay. Hopefully not too bad. Okay. All right, let me give you a couple more just so you can see what's going on here, okay? Everybody okay if I go to the next slide? Okay. I'm just going to make a silly one up here, okay? So let's define the random variable x be equal to the number of cups of coffee Matt has on a random day. Okay. So imagine I have this like spreadsheet, okay? And it has every single day from last year on it. And what I have there is I have the number of cups of coffee I had on that day, okay? And so what you're going to do is you're going to randomly select a day, okay? So the x, the value x takes on would be determined by chance. Okay, so let me just tell you, do you guys think I have a cup of coffee every single day of the year? Do you ever think I miss a day or two? Let me ask you this. I try not to. Okay, I really try not to. My wife always jokes around and she says, if I'm in a bad mood in the morning, she'll always ask me, and I'm not even kidding with you. She'll always ask me, she'll be like, Matt, have you had your coffee yet? Okay, I even think she asked me that this morning, because I didn't have my first cup of coffee for a couple hours. But every once in a while I have 0 cups. Maybe I have 1 cup, 2 cup, 3 cups. And I cut myself off after 4 cups of coffee. I never have more than 4. Okay, it gets ridiculous at that point. So look, let me just give you the probability of each. The probability that I have 0 cups of coffee, it's really low. It's like 5%. Probability I have 1 is 15%. Probability I have 2 might be 20. Okay. And then the probability I have 3 is 30, and the probability I have 4 is also 30. So just by looking at this, you have to ask yourself, is this a probability distribution? Okay. And so the big thing that there's only 2 rules you need to have. Okay. So I'm going to go back real quick. The individual probabilities are between 0 and 1. And when you add up all the probabilities, they sum up to 1. So are all my probabilities between 0 and 1? Yeah. Okay. And when I add up all these probabilities, do they sum up to 1? Yeah. Yeah. So this is a probability distribution. Okay. Let me just do one last thing here. Okay. Everybody okay? I'm sorry. Is everybody okay if I go on? I hope so. Okay. Okay, so what's wrong here? So suppose I give you this probability distribution. So I say the random variable X can take on the following probability or following values: 0, 5, and 10. And the corresponding probabilities are 0.25, 0.63, and minus 0.02. All right, why could we say this is not a probability distribution?
It doesn't add up to 1.
What doesn't add up to 1?
The 0.25, 0.63, and negative 0.02.
Yeah, and also, can you have a negative probability?
No, we cannot.
Okay, so let me ask you this then. Is it okay? Like if you look at all my previous examples, the numbers went in order. It was like 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4. Here I went 0, 5, 10. Do you think that's okay? The numbers, just they go from 0 to 5 to 10?
Yes.
Yeah, it's totally. If you look back at the rules, there are no rules for the value X takes on. Okay. So X doesn't have to be like perfectly in order. Okay. What's really important is that the rules of the probability hold. Okay. All right. I just want to end class talking about a probability histogram and then just doing one example of it. And then we'll be done for the day and we can go right on to our weekend. Okay. So just a final definition for the class. A probability histogram and just so we're clear on what this is the visual representation of a probability distribution. So a probability histogram is a histogram in which the horizontal axis corresponds to the value of the random variable. So what that means is the horizontal, the flat axis, the x-axis, just going back real quick, corresponds to these x values. And the vertical axis corresponds to the probabilities or the probability of the random variable. Okay, so I'm never gonna quiz you on this. Okay, I just want to do one quick visual representation of this because histograms and visual representations of probability distributions do come up again in the class. So let's just sketch real quick the probability histogram for the coffee example. Okay. Like you guys can see my video, right? Real quick. Like I'm finishing my 4th cup of coffee today. Okay, today was a big coffee day. All right, so what I'm going to do is I'm just going to rewrite the probability distribution real quick. So I could have 0, 1, 2, 3, 4, or 5. And I think it was 0.05, 0.15, 0.2. Oh, I stopped it. Sorry, I had an extra one there. 0.2, 0.30, and 0.30. So to sketch the probability histogram of this, you're just going to draw the first quadrant of the Cartesian plane. And what goes along the horizontal axis are the values of the random variable x. So it's literally 0, 1, 2, 3, or 4. They just build right next to each other. And then you're just going to have the corresponding probabilities along the vertical axis. So 0.10 or 0.05, 0.10, 0.15. I'm sorry, it's a little sloppy. 0.20, 0.25, and 0.30. Yeah, go ahead, Bertha. I'm sorry.
Why is the 0 there? Shouldn't the 0 be like at the corner, at the left corner?
So the reason it's not in this case is just because like you need a whole bar to represent 0. So like 0 is going to be more than just like this straight line here. So that's why. It's not like it needs to be perfectly like lined up with this 0 axis here.
Thank you.
Yeah. And then all you're really just going to do is draw the bars up to the corresponding probabilities. And really what's going on here, if you think about it, 0.20, is this is just a relative frequency histogram. That's all this is. And we've done that before. And so just what this shows is it just shows like, look, you know, the probability that I would drink 3 or 4 cups of coffee is much higher than if I were to drink 0. That's it. That's really what it's just a visual representation of this table right here. And so what we're gonna do next class, on Tuesday of next week, what we're gonna do is we're gonna talk about this concept called expected value. And I actually think it's a real fun topic. And then we'll start the binomial probability distribution. So just going back to your homework real quick. If you wanted to try finish off your homework, you can do every problem on your homework this weekend except you cannot do number 7 and number 8. Okay, you can do every other problem. So I encourage you to tackle this problem, this homework over the weekend and come to questions the class on Tuesday. So that's it. That's all I got. Does anybody have any final questions for me before we call it for today? No questions? Okay, so what I'll do is I'm gonna post the PowerPoints to Blackboard. Let me stop the recording.